Last class we looked at the various elements in the IC circuit. So, today we are going to look at how these elements come together to form your typical integrated circuit. So, we are going to look at IC circuit logic, and we are also going to look at packaging. So, packaging refers to the fact that when you have the final die or the IC circuit made, how it is then integrated as part of your system. So, this system could be your laptop, it could be a desktop, could be a mobile computing device, any of those. So, some of the circuit elements we saw in last class. We looked at resistors or conductors, capacitors, diodes, and then transistors. So, these can be divided to two main types. So, resistors and capacitors are essentially called passive components, while diodes and transistors are called active components. Both of these come together to form your final IC circuit, and VLSI design mainly deals with how we arrange these different elements to form your IC circuit. Now, VLSI design and silicon micro architecture by itself is a complete course. So, obviously, we will not be covering that greatly in detail, but what I wanted to do was to show a flavor of how the various components that we saw come together in order to form logical and arithmetic calculations. So, when we think of a computer, the basic logic behind it is called your binary logic. Another name for that is also called Boolean algebra. So, according to this, there are essentially two states in your system. So, these states are denoted as on and off, or you can denote them as true or false, or even ones and zeros. So, the advantage of using a Boolean algebra is, especially when you think of an on and off kind of state, you could have a high voltage being an on state and a low voltage being an off state, and this can be controlled by controlling the voltage across the circuit. So, in the case of Boolean algebra, any number can be represented as a series of ones and zeros. So, any number becomes a series of ones and zeros. To give you an example, if you take the number 7, 7 can be written as 4 plus 2 plus 1. So, since Boolean algebra has only two states, it is basically written in powers of 2, and 4 can be written as 1, 2 square, 2 is 1, 2 to the 1 and 1 is 1 times 2 to the 0. So, 7 essentially becomes 1 1 1. If you think of the number 6, 6 is again 4 plus 2 plus 0. So, 1 2 to the 2 plus 1 2 to the 1 plus 0 times 2 to the 0. So, 6 essentially becomes 1 1 0. If you think of a higher number, you may have to go with a longer string of these, but essentially anything can be broken down into ones and zeros, which represent on and off states, and these again can be represented by voltage fluctuations. Each 1 and 0 is called a bit, and 8 bits come together to make a byte. There are higher orders as well. There are kilobytes, megabytes, gigabytes and so on, which all represents higher orders of these bits. So, using Boolean algebra, you can do both arithmetic calculations and also logical operations. So, when you think of arithmetic calculations, you can do things like addition, subtraction, multiplication, division and so on. You can also do higher order arithmetic calculations as just based upon these. You also have various logical operators. So, typical logical operators are AND gates, OR, NOT, and then variations like NAND, which is NOT and an AND gate, and so on. So, these operations can basically be performed by using your diodes and transistors, which are your active components, and the currents through these can be modulated by using resistors and capacitors, which are your passive components. So, we will look at one very simple example. We will consider an OR gate, and we will see how we can execute this OR gate using simple diodes. So, we look at an OR logic gate. Just based on the name, we can see that the output will be high, and high we can represent by 1 when either input is high. So, we have two inputs 1 and 2. And then we have an output. So, if both are 1, the output is 1, but if either of them is 1, so if either is high, the output is also high. So, 1 0 gives you 1, 0 1 gives you 1, and only when both are 0 is your output essentially 0. So, it is possible to construct an OR gate which displays this characteristics. This is essentially called a truth table by just using two diodes. So, let me draw the circuit diagram. A diode is nothing but a PN junction, and last class we saw how we can fabricate these PN junctions. So, I have two diodes and two inputs A and B. So, this is my diode 1, this is diode 2. Both are connected together and there is an external resistor R to modulate the current in the circuit. Then you measure the output Q. So, if either A and B are high, which means your diode is in a forward bias conditions, you will be able to measure a current or you will be able to measure a voltage drop across Q. So, your output is 1. Only when both A and B are turned off. So, you can think of this as a reverse bias condition, there is no current in the circuit and then the output is 0. So, just like an OR gate, you also have other gates like AND, NOT, etc., which can be implemented using simple diodes. You could do the same using transistors. We will not talk about the circuit implementation using transistors, but something similar can also be done. And since all of these are essentially fabricated devices, we can essentially fabricate these simple logic gates onto your wafer. And if you think about it, an integrated circuit consists of a whole bunch of these active and passive elements. So, all of these can be fabricated onto your wafer to give the desired logic. Similarly, arithmetic operations, so a simple addition, subtraction, multiplication and division can also be performed by using these diodes and transistors and how they come together in order to give the final result. Another important component of any integrated circuit is the memory element. So, memory elements are essentially either static or dynamic. A static memory element is one which once it is written can be stored. On the other hand, a dynamic memory has to be constantly refreshed in order to store the particular value. So, memory elements can be made using transistors. So, to give you an example, consider a dynamic memory element. A simple schematic of this shown here. So, you have a capacitor that basically stores a charge. So, the capacitor can act as the storage of memory. So, when the capacitor is charged, you could have a certain value written to it. For example, it could be 1. When the capacitor is discharged, then the value goes back to 0. But capacitors essentially tend to leak charge. So, they constantly need to be refreshed, which is why this is a dynamic memory. Whenever you have a memory element, the memory element also needs to be read, and this is done by using your transistor. So, this is called your access transistor. You could also have static memory elements. So, So, this does not need to be refreshed. So, these are formed by using multiple transistors in order to store and retrieve the information. So, multiple transistors So, it is possible to build both the operative part of your IC circuit, so logical operations and arithmetic operations. It is also possible to build memory elements, again using your transistors and capacitors, so again your active and passive components. All of these come together to form your integrated circuit. So, microprocessors, if you think about it, are circuits that combine both the logical and the memory units. So, the logical refers to that part of the circuit that does both the logical and the arithmetic calculations, and the memory units correspond to that part of the circuit that basically stores the input and also the result, and that can be retrieved whenever needed. So, the first microprocessor was built in 1972. It is basically built by Intel. It was essentially a 4-bit processor which meant each element was essentially stored with 4 bits. So, earlier we looked at the number 7 and we represented 7 as 111. If you are trying to do the same using a 4-bit processor, then it just becomes 0111. So, this was the first microprocessor that was built. Now, we have processors that are essentially 64-bit long. Now, we have 64-bit processors. So, the same number 7 can be written as a 64-bit number, but essentially all the leading elements would be zeros followed by the last 3 1, 1 and 1. So, we have looked briefly at the IC circuit logic. The next thing I am going to look at is packaging. So, how we take the final die and then package it so that it can become the part of an external circuit. So, we are going to look at packaging. We can define packaging as a set of processes that provide protection to the chip. That is one of the functionalities. But more importantly, it allows the chip to be integrated to a larger system. So, there are essentially two main paradigms by how this is implemented. The first one is called a system on chip. Short form is SOC. So, in this case all the various components are integrated onto one chip. So, it essentially becomes a fabrication issue, how you fabricate the different components onto the single chip. To give you an example, desktops usually have things like an integrated video card. So, this would be an example of a system on chip where the video card is integrated along with the main microprocessor. The other paradigm is called system on package. In this case you have different devices with specific functionalities. Which are integrated on a package. For example, you could have a microprocessor, you could have a video card which would be an external video card, you could have audio devices, so input output audio devices, all of this having specific functionalities coming together onto the package to form your final system. So, when we look at the packaging process, the chip characteristics that basically affect packaging So, the first one is the integration level. So, this refers to whether you have a system on chip or a system on package. It also defines things like how many leads you have and how many connections have to be made and so on. The wafer thickness. So, later we will look at the various steps in the packaging process, and one of them is to actually thin the wafer down, so that when you start with a wafer that is typically 700 microns thick, it is thinned down to a few hundred microns, so that packaging becomes easier. Then the dimensions. So, dimensions again refer to how many leads you can have, how closely spaced these are. So, this is related to the die size, which is again related to the type of chip you have. Then environmental sensitivity. So, this is related to the fact that the original solders that were used were all lead based, because lead is essentially a low melting point, but lead is also poisonous, so that the process by itself is highly hazardous. So, now new methods are being developed in order to have lead free packaging. Another one is the physical vulnerability. So, it refers to what are the physical conditions that are encountered by the system during operation. For example, you could have a microprocessor being embedded in a machine that is under constant use, so that both stresses and strains and vibrations would all play a role. Some of the other characteristics are heat generation, and heat sensitivity. So, the last two are essentially important because we find that as we go with higher levels of integration, so that we have more and more transistors that are being packed in smaller and smaller areas, it basically tends to generate a lot of heat. Simple way to think about heating is that if you have a resistor and you pass current through it, you have something called Joule heating, which is directly proportional to the square of the current and also directly proportional to the resistance. So, more the circuit elements there are, more the heat will be generated, and this in turn can affect device performance. So, the amount of heat generated and the sensitivity of the device to heat is also essential in determining how we package it. So, usually there are ways provided in order to dissipate the heat to minimize any effect on the wafer itself. So, we will look next at some of the functions and designs of the packages, and then we will look at the series of steps that go into the packaging process. So, there are 4 basic functions for a package. So, the first one is to provide substantial lead system. So, these leads are electrical leads which are used to make connections to the rest of the package. Physical protection, the ruggedness of the packaging process, environmental protection, and then finally heat dissipation. Heat dissipation is especially important if you have mobile computing. So, think of the fact that you have tablets and cell phones. So, all of these again have microprocessors. So, heat dissipation is very important in these, because these again can lead to heating up of the device, which is something we all do not want. So, this is especially important for mobile computing. So, there are various ways of implementing this. So, one way is at the fabrication level itself to come up with a micro architecture that essentially uses low power, so that the amount of heat generated is small, but you can also address this at the packaging side, so that you have proper heat dissipation in your system. So, earlier when we saw the fabrication process, we figured it as a series of processes in terms of an assembly line. We saw the wafers go from one step to the next in sort of an assembly line fashion. So, similarly we can look at packaging as a series of steps, so that the final wafers, the dies, go through these series of steps in an assembly line, and at the end we have the final package. So, the first step in the packaging process is your backside preparation. So, this is typically a wafer thinning operation. So, if you look at it, a typical wafer dimension has thicknesses somewhere around 500 to 700 micrometers depending on the wafer diameter. So, a typical thickness somewhere around 500 to 700 micrometers. This is thinned to approximately 100 micrometers by some sort of chemical mechanical polishing of the backside. So, the front of the wafer is protected usually by applying some sort of a coating, and then the back side is thinned, so that the overall thickness comes to around 100 micrometers. So, this is helpful because it can then be used to easily separate the different dies from the wafer and then package them individually. The original high thickness 500 and 700 microns is essential because during fabrication the wafers go through a whole series of processes. So, they should be mechanically robust, which is why they are originally thick, but when it comes to packaging, the thinner the better. So, after backside preparation, the next step is die separation. So, in this the individual dies are separated from your wafer. So, typically this is done by a sawing process or a scribing process. Usually you use a diamond based system. So, you have a diamond saw or scribe. So, this is used in order to separate the wafers. So, just to give you a schematic, this represents your wafer. We have seen the concept of scribe lines earlier. So, scribe lines basically separate the different components of the die. So, sometimes the scribe lines are blank, but they usually have some circuits for electrical testing. So, these are your scribe lines, and then the dies are fabricated on the top. So, the wafers are separated along the scribe lines again by using a diamond saw or a diamond scribe, so that you get the individual dies out. This is the die separation process. After that we have die pick. Again, after die separation, the good dies are essentially picked and the bad dies are discarded. So, we saw this earlier. So, this goes into the yield of the process. So, the more good dies we have, the higher is the yield. Then we have die inspection. This is more of a physical inspection to check for any cracks or defects, because during the packaging process there will be further stresses on the dies. So, we want to make sure the dies do not fail. So, these dies are those that have passed the pick process. So, they have passed electrical inspection, but this is essentially a physical inspection. The next process is the die attach process, because the die has now to be integrated along with your chip. So, you have a die attach and then a bonding process. So, this is essentially the most important part in the packaging process, the bonding. So, here the die is bonded to the package and also the leads are attached to make the electrical connections. So, there are different ways in which bonding occurs. So, we will see that next. So, we will look at the bonding process. One method is called the wire bonding. So, in this case either gold or aluminum is used. So, if you recall, the bonding is done to mainly form the electrical connections to the external circuit. So, in this case either gold or aluminum is used to form the electrical connections. So, to give a schematic of this, here is your die, there is a pad for essentially making the electrical connection. So, that goes to how the metallization occurs. So, when we looked at the metallization, we saw there were different levels of metallization. So, some of the newer transistors or newer IC circuits have essentially 11 levels of metallization. So, the connection is made to the topmost level. So, these in turn feed back to the transistors and the other components of the IC. So, you have a bond that is being formed. So, the wire is fed through some sort of a capillary system. So, this is the capillary, this is the inner lead, and this refers to the bond. So, in this case the gold is fed through the capillary and by thermocompression it basically forms a bond with both the die and the lead. In the case of aluminum, you could use a similar process. Sometimes an ultrasonic agitation is also used to form a bond. In that case it is called a wedge bond, but a similar bond can occur. We also have something called a tape bond. It is mainly used for extremely thin devices. So, as here your bonding is usually in the form of tape, which are again bonded to both the lead and your die. But recently when we have these IC circuits with a large number of leads, where a large number of connections have to be made and the leads are also closely spaced to one another, a newer method of bonding is being developed. This is called a flip chip or a bump and ball bonding. So, this is currently being used in the IC industry due to the large number of leads and they have to be closely spaced to one another. So, in this particular idea no wires are used. This is your schematic of the die. So, in this case a solder material is melted and then flowed on to the connection. So, this is your refold solder bump. So, all the different connections or all the different leads that have to be made, a solder material is essentially melted and then flowed onto it. The entire chip is then flipped, which is why it is called a flip chip, and then the leads are directly bonded to your package. So, the chips are flipped over and directly connected to the die. So, another name for this process is called the controlled collapse chip connection. Or C4. So, there is no separate die attach and bonding process, both the bonding and the die attach is done in one step by using these reflowed solder bumps, which are inverted and then directly bonded to your die. So, after making the bond there are a few final steps. The one is your pre-seal inspection. So, if the bonding process is number 6, your pre-seal inspection is 7. So, this again looks at the electrical functionality and the reliability of the bond once the bonding is done. So, this is after bonding. Then the package is sealed. So, you have a sealing process. Sealing can either be a hermetic seal. So, in this case you make sure there are no external atmospheres that come into the package. This is essentially important for environmental protection. You can also have non-hermetic seals. So, sealing can be hermetic or non-hermetic. Then you have the lead plating, lead trimming, package marking, and then the final testing. At the end of the final testing, the package is ready and it can then be integrated either onto your system. So, it could be a part of a system on a package deal, or it could be a package where all the components are already integrated into it and then it becomes a system on chip. So, these are the various steps that go into the packaging process. So, once again you can think about it as an assembly line where the final dies go through these series of steps in order to give the final package.